what I'll go over first is, well, okay, how do left-leaning red-black trees work? So there are three main rules, okay, that you must know to understand left-leaning red-black trees. So I'm going to start off with the first rule. If there is a right-leaning node, rotate left. Okay, before I even go there, I want you guys to constantly see and notice the translation between a left-leaning red-black tree and a 2-3 tree. This LLRB right here is the same thing as B, D, A, C, E. Okay, so this red node, like these two pretty much got connected into a 2 node. But we want trees to be left-leaning to ensure that our data structure is as complete as possible. Okay, similar to the way we use complete BSTs for priority queues, you want to push everything to the left so that we get a tree that is as complete and bushy as possible. If there's a right-leaning node, you call rotate left on the parent, okay, on the parent of the red node, okay? In this case, the parent of the parent of the red node is the parent of D, which is B, okay? So how does rotate left work? The first step, you swap colors. The second step, you temporarily detach B's left child. So the left child becomes like quote unquote an orphan. Then step 3, A becomes B's left child. And then the fourth step is A quote unquote adopts B's orphans as A's right child. Okay, that was a lot, and now I'm going to show that. Okay, so the first step is to swap colors. The second step is to temporarily detach the child. So B in this case, the child is going to be this one. So temporarily detach the left children. So I'm going to temporarily detach those children. A becomes B's left child. So what happens here is B moves down, okay, and becomes the left child of D. So a better visual is now D's left child is going to be B, okay? And then B is going to inherit or adopt the original left children of D. So then C is going to be the right child of B. Let's convert this into a 2-3 tree. So this is going to look like B, D, A, C, E. And if you guys will notice, that is the exact same thing as we had in the beginning, okay? But in this time, for this tree, we are maintaining the LLRB invariant, meaning that all red nodes are left-leaning, okay? The second step is if there are two consecutive left-leaning nodes, rotate right for the parent node, okay? So the parent node in this case is going to be D. So I'm going to call rotate right on D. Okay, so this is tricky. How does rotate right work if I call rotate right on D? So essentially what happens is C moves up, okay? C will move up and become the right child of B. And D will move down and become the right child of C. Okay, where now these, okay, again, we're going to also, like the one before it, like the method before it, we swap the colors of the parent and the first left-leaning node. So D is now a red node and C is now a black node. You swap colors, you temporarily detach the B's right child, A becomes B's right child, so B becomes the child of A's parent, and then A adopts B's right child. I think this example is better for clarification. Let's translate these to 2-3 trees. So what this looks like as a 2-3 tree is B, A, and then we have E, C, D, right? Here is the same thing. We have B, A, E, C, D. Okay, what's the problem here for 2-3 trees?
It's the same as before. There are 3 values, so it can have 4 children?
Exactly. The problem here is that this node is too full. It's a 4 node because it can have 2 children. I mean, because it can have 4 children and there's 3 values inside of it. So if this is the case, if we have a 4 node, meaning we have 2 red children, we will call a method called color flip on the parent, okay? So in this case, the parent of the 2 red children is this C. So we call color flip on C. And what color flip does is pretty much exactly how it sounds. You flip the colors. So C becomes the red node, and then both E and D become black nodes. Okay, so now if we translate this into a 2-3 tree, it will look like this is a valid 2-3 tree. So we're happy. So we consider the following red-black tree, and I want you all to draw the tree after applying all necessary fix-ups to make it a proper LLRB tree. So let's go over this together. So I redrew the 2-3 tree here. So this is what we are starting with, okay? So we have 2, 1, and in red would be 6. In red would be 0, 4, 8, in red 3 and 9. So the first problem that I see, okay, is that we have a right-leaning node, this 9 right here. So like I was talking about in the 3 rules for LLRBs, the first thing we're going to want to do is call rotate left on the parent of 9. So we're going to call it on 8. Okay, so we go through the rules of swapping the 2 colors and then making 8 the left child of 9 and 9 the right child of 6. And that is shown here. Okay, so 9 became the right child of 6 and 8 became the left child of 9, and the colors also swapped. Okay, then I see another issue. Okay, I see that we have another right-leaning node, the 6. And so I'm going to call rotate left once again on the parent 2. And so what happens there is 2 becomes the left child of 6 and will adopt 6's old left children. So what that looks like visually is this. We have 6, then 2. You see how it adopts the 4 and 3. And 6's right child will be the same as it was before. But now this tree holds to the LLRB invariance. Okay, any questions there? As a 2-3 tree, this looks like 2, 6, 1, 0, or 0, 1. The 2's left children is going to be a 3, 4, and then the right children of 6 will be 8, 9. Okay, so that's what this LLRB is as a 2-3 tree, and it's balanced. Okay, the next problem is inserting 10 into our tree. Okay, I forgot to outline this before, but when we insert 10, when we insert any number, we want to insert this as a red node. The reason for that is, well, let's draw this tree as a 2-3 tree once again. We have 2, 6, then 0, 1, 3, 4, and then 8, 9. Okay, this is what it looks like before. And then if we were to insert a 10 here, we would just append it here. Okay, so it's still part of this node. So now this node is too full. And so this is what it is represented as in a 2-3 tree. And so now we're going to go through the process of taking this 4 node, this node that's too full, and properly making the correct color flips and switches to make it a proper 2-3 tree. So because I have 2 child nodes that are red, I have to call flip on the parent, which is 9. So I do exactly that. So then we have 9 is red, and then 8 and 10 are black nodes. But then I have another case right here where 2 children are red nodes. So I have to call flip again on the parent. So I call that on 6. So I call it here. And that's what that looks like. So also I'll show that again. So we have the 2 and 9, which are red nodes. And then when you call flip on 6, 6 becomes the red node, and then the 2 and the 9 become black nodes. Okay. One other thing I forgot to mention is that if you have a red node at the very root, this is logically equivalent to having 6 just be a black node. So I just removed the red part for the 6. Now, the reason that is because red nodes are a way to describe a relationship with a parent, but in this case, 6 has no parent, so it's equivalent to it just being a regular black node. Okay, now to describe this as a 2-3 tree, we pretty much go again. So we have a 6, 2, 9, and we have a 2 node here. So we have 0, 1. We have a 2 node here, 3, 4. These are single nodes, 8 and 10. And you'll notice this is balanced.